Congratulations. All right. For those, sorry, the stream wasn't working. So just to recap real quick, 3 study materials on web courses. Mixed problems, set with the problems mixed together. Test to review, overviewing everything. Click your questions. Test is in 1 week. There you go. TLDR. So there you go, y'all. Prepare, do well. In my opinion, okay, I don't even have to say my opinion. Statistically, students do better on my second test than my first test. You can argue there's reasons why. 1, you're better, you know the structure. 2, the content. I would argue that the content on test 2 is easier than the content on test 1. You're not working with vectors all the time, but again, people have different opinions on what's easy. What I will say is, yeah, hopefully you're better at physics on test 2 than you were in test 1. You've been doing it for longer. So that's probably the biggest reason. All right. Let me remind you all of what we covered last class, which is center of mass. We're going to do a lab on center of mass today, which hopefully helps you kind of get a feel for it. So I gave you all this problem. This is how I introduced the idea of center of mass to you. Where do I place a vertical beam to support this weird triangle shape? And the vast majority of you all said B, and you're correct. And why is that? It's because there's a magical thing called center of mass where you can approximate all the mass to exist at that spot. Angelina showed you all a cool video of like the tennis racket getting thrown. Even though the tennis racket is spinning and it looks like a hot mess going through the air, when they put a dot at the center of mass, it was just a nice parabolic path because you can approximate all the mass to exist at that spot. Center of mass is an extremely useful thing if you're ever building any physical system. You pretty much have to know where the center of masses are for various objects. And there's then I talked about, so there's the video. Oh, I added a video of this actually to the slides. So that's there now. I then tried to convince you all this is something that you're actually familiar with, which is a weighted average. So I gave you all an example with grades, and maybe you haven't done GPA calculations before, but whatever, we did one of those to show it's just a weighted average. It's the exact same thing. And then we did a 2D problem with this, and it was a good time because remember, it's in the X and the Y. And there is 2 examples I want to mention to you all today that I thought about this morning. I was like, oh, I should mention these because these are really good things. You know, I'm just going to ask you the question. If you lean forwards, what do you have to do to not fall down? And let's just say you're standing. If you are standing and lean forwards, what do you have to do to not fall down? That is my question proposed to you all. Think about it, discuss with your neighbors. I'll walk around and hear what y'all have to say. If you want to test it, literally stand up and lean forward and see what you physically do. You do this naturally. Do it for yourself. You got room? How do you not fall down when you're leaning forwards? Stand up. Try it out. If you're like, I don't know, stand up and try it out. How do you not fall forward? Okay, your arms back. You keep leaning forward. You do have to take a step. I don't want to take a step. How do you balance? Go ahead, do it. It's something you naturally do. Don't think about it. You start thinking, if you had to balance, you want to shift your face forward. Your arm is one thing. Probably more than that. I'll show you. Interesting enough, you have other limbs at your disposal. All right, what'd y'all say? What do you do? How do you balance? How do you balance? What is your body? What do you physically do with your body? How? Spread your feet across? That's not going to help you. Move backwards. Oh, you could put a foot back there. Yeah, what are you doing?
Making my lower half stronger.
How are you balancing? What physics is going on there? Why does that balance you? Why does putting it backwards?
I'm pushing force against the ground.
Yeah, because the ground's actually going to push you farther forward, so you don't want to push forward. You're changing your center. Yeah. Yeah. All right, just to showcase you all, what's the way that you balance forward? If you ever really want, say you want to pick something up off the ground, but you don't want to lean down all the way. What do? You stick your leg out. Like, look, if I put my leg down, so here's my leg up. If I put my leg back down, I fall. Why? I have literally. What is the only point of contact with the ground? My feet. So here's something, if you've never thought about this, it's a really, really interesting thing. So here's you. Right now, where's your center of mass located? When I'm standing up like this on the picture, where's the center of mass located for this person?
Around their hips.
Around their hips somewhere. There you go. Let's just put it right there. Let's say that person starts to lean forwards. Where is their center of mass now? It is right here. Here's the problem. Gravity pulls down on that center of mass, which causes you to fall. So, how do you counteract that? Here's the really, really interesting thing about balance. Everything to do with balance, you have to shift the center of mass above the place where your feet are actually touching the ground. If the center of mass is in front of or behind your I don't know what you want to call that, fulcrum, like the point of contact with the ground, you will fall. Like, that is how you fall. That's the reason people fall, is their center of mass is shifted forward. So even when you might not even realize, even when I bend like this, something you are very subtly doing is sticking your butt out the other way. You may not realize this, but when you bend forwards, you stick your butt backwards. If you don't, say I just tried to, gosh, you can do this yourself. Literally, like, you can't do it. If I try to stand completely straight and just bend my forward, I will fall. There is no counteracting that. It's a force problem, y'all. Force of gravity is pulling your body down. So we're going to learn about torque eventually and stuff like that. How do you counteract that? You need a force going upwards. None of your shoes are sticky. No one's wearing shoes that stick them to the ground. So, why is center mass? So what do you do to counteract this? You stick a leg out, and it moves your center of mass above the contact point. This is why center of mass is so important. If you're designing anything and you don't want it to teeter over or fall over or have stress and strain on your system and on places that you don't want it, you need to be able to shift the center of mass, and you are doing this all the time. If I move my legs far apart, left, right, does that help me at all, leaning forwards or backwards? Because X and Y are independent of each other. You've changed your Y center. You've changed your Y center of mass. That does nothing for your X center of mass. So there you go. Really, really useful real world application of center of mass and why it's useful. All right, attendance time. Yeah, every single object, y'all, when they design it, they have to design it so the center of mass is above some structural point, or they have to have some really strong bolts in place.
I think I might take physics 3 more semesters. I like it.
Yeah, sure.
It's fun.
It is a good experience.
Sign up to do it again.
Yeah, I'd be fine with that. I'd be on board with having the same person.
As long as I did well.
I appreciate that. All right, gonna leave this for a few more moments. I don't see any phones. I see one phone. Oh, wait a second. All right, cool. All right, so. Was that too slow? All right. So another thing to keep in mind now is whenever you all look at stuff, whenever you all walk outside now, look for things where their center of mass is not above like a support column. So like a really easy example is when you're on the road, when you're driving on the road and they have those signs, I'll make them big and green because that's the way they look. So you all know when you're driving like the highway and they have the giant signs with like instructions and stuff like that. Like this road is this many miles away. They hang above the road. Sometimes they'll have a support column on both sides, at which point the center of mass in the middle, but they're both kind of bearing that load. Other times they don't. And so the question is, why isn't this falling over? And this is civil engineers have to design. This is bolted to that. And then this thing is buried in the ground / bolted. It's buried in the ground a certain amount. So even though there's a force there, there's also a force that's going to oppose it from the ground. We're eventually going to learn about something called torque. Torque is there anytime things rotate, which is something falling is just something rotating. That means there's a net torque acting on it. If it's not, and then it does, we'll get to that after the test. But it's a really interesting thing. Center of mass shows up all over the place, and civil engineers especially have to really care about where the center of mass of the structure is. If y'all take statics is all about net torque equaling 0. And center of mass plays into that. Okay. The last case of center of mass I want to talk to you all about, and this is one we're going to see how much you know about cars. How do they balance? What does it mean to balance a tire? And how do they do it? This is hopefully someone in your group knows something about balancing tires. This is something they do whenever you get your tires changed or things like that. Whether you realize it, they're doing this. They're balancing your tires. They have to. There's reasons. What the heck are they doing? Ask around. Hopefully someone in your group knows. If not, start Googling things. If you drive, this matters to you. Oh, you don't drive? Oh, I'm still looking around for. That's our conversation. Is the used market not good right now? Is the used car market not good?
Everyone wants to rip you off. It's hard to find.
All right, so balancing a tire. Let me find a quick video. Oh, this is gonna be weird. I don't know if this does weird things for me. I'm gonna find a video of balancing a tire while I'm streaming my thing. All right. This is really all I needed was a picture of it. So if y'all look at the second one, I really just need the picture. They put your tire on this thing and they spin it really fast. Why do they do that? Someone else, see if anyone knows. Yes. To see if it wobbles. Do you want your tire wobbling on your axle? No. That introduces additional strain upon the axle, which will eventually degrade things. Why does it wobble? Why would your wheel even wobble in the first place? because it's not balanced. But in terms of the words that we're using today, its mass is off center. If you're tired, so one of the things with center of mass, things want to spin around the center of mass. They will spin freely around the center of mass really nicely. Think of a fidget spinner. It's nice and symmetrical. It's got the three kind of lobes on it. It spins really nicely around the center. If your tire has a center of mass that is not in the center, so this red is the center. Let's say the green is there. It is going to wobble. It's going to want to go around that green center of mass. It can't because of the axle, and it will put strain on it. So how do they fix the wobble? They have weights. Where would I put weights in this picture to shift the center of mass? You would move it. You put some weights over here. What do putting weights over there do? They shift the center of mass to the center. So they have a piece of equipment that basically is detecting where the center of mass is, and then where do they need to put masses to shift, and how much mass. It's a center of mass calculation. Like they might do it doing other things, but that's effectively what is going on here. This is another reason why center of mass is so useful. Anything that rotates, you need it to rotate really smooth. You all can have things rotating it. Like a tire is one thing, and that is dangerous if that thing gets off axis. But say you have like a drill bit. If you rotate a drill bit and that thing is not centered right, they can literally like explode into a bunch of, like the amount of strain on the system if something is not centered correctly and it's rotating at thousands of RPMs can be extremely dangerous. It can literally tear apart things that are metal or things like that. And then you have shards going everywhere and your thing broke and it's really bad. So if things rotate, you need the center of mass to be dead centered. And there's a lot of things that rotate in this world. Like, I mean, just look at, yeah, the world. The world does rotate. And that's a really interesting kind of thing to think about. And the mass of the earth can kind of redistribute itself in some ways to accommodate that. Oh, the earth does wobble, which, yeah. So that's a whole nother, yeah, you got precession and weird things. All right, anywho. So there you go. I hope I've just conveyed to you all the importance of center mass, why we're doing it, why we're spending the time on it. Okay, I got a single clicker question today. Oh, no, I got two. There you go. All right, this is the same problem as last time. The same problem, but be careful. It says if the 75 kilogram mass was instead 6 centimeters above the 150 gram mass, what would happen to the x component of the center of mass? Draw a picture if you need to. Draw the original, draw the final. How would the x component of the center of mass change? Would it shift to the right? Would it shift to the left? Or would it stay the same? Yeah, I should have added more options on here. I should have put shift up and shift down. There's a little bit of hints in the answers. All right, we'll go for 10 more seconds. Either you know it or you don't. All right, in 5, 4, 3, 2, 1. Yeah, you could totally do all the math. That would be terrible. You could do the math for this problem and get the answer. I'm going to, through the magic of copying the problem and stretching it. Now it's 6 centimeters. All right, so we actually found the center of mass of our old system. Where is it? Our center of mass for this one was at negative 0.0123 and 0.069. All right, so our center of mass was, I don't know, something like here. So where's my new center of mass? Something up here. Did it move left or right? No. This is an exercise in XY independence. If I move things up and down, why do I care about the X? I don't. If I move it up, and let's see what it looks like. Shifting it upwards has zero effect on the X component because I didn't change any X components of anything. If y'all look at the equation for the center of mass of the X, it's all has to do with X coordinates. All the X coordinates are the same. So, be careful. X and Y are independent of each other. All right. Now, great. We got point masses. Hopefully you feel somewhat comfortable with point masses. Let's make it worse. The real world, okay, you can't approximate things as point masses. But let's go back to our original example. The triangle. Behold, a thing that is made up of a million, bajillion, quadrillion point masses called atoms. Yes, if you really wanted to, you can do center mass calculation by doing the individual atoms and where they're located. And that's awful. We're not going to do that. That's crazy. But if you want to sum up an infinite number of things, what's our symbol for the sum of an infinite number of things? It's an integral. So, this pretty picture I've drawn here is two things that represent the same thing. As weird as this looks, we're not actually going to solve the triangle problem, by the way, because you could do it, but it'd be a little bit more we're not going to bother with it, but it's just a good example to show you all. If you all look at this triangle, where is the most mass found? On this side. So this little gradient just shows you the mass distribution. Where the triangle is thicker, there's more mass. Where the triangle is thinner, there's less mass. And so we have a distribution of mass. We have a distribution of mass. Now again, I'm not going to have y'all, you could then find how that mass distribution varies and do things and all that kind of jazz. But I'm going to tell you all, this is more so the one that we're going to be kind of working with. An object whose mass varies, but its shape doesn't. An object whose mass varies based on location, but its shape doesn't. And I'm going to give you all I'll give you all 10 seconds to see if you can figure out. Let's see. Are we going to, okay. Yeah, see if y'all can, this is just a foreshadowing of things to come. What the heck is the word for how your mass changes based on where you're located? Let's go with that. What's a word that would describe how much mass you have in a specific locations? How concentrated the mass is, if you will. Think about it. Give y'all 30 seconds. See if y'all can figure out the word. It's a word you've heard before. I guarantee you every single person in this room has heard the word. Almost guaranteed. And it's a foreshadowing of things to come. What is the word for how mass varies based on how concentrated? Yes, the gradient of mass don't actually do it. This is a word that how mass varies. It's a measure of the concentration of mass. Alright, you all say the word, you all get the word. Alright, we're gonna use that somehow. Alright, great. Foreshadowing of things to come. Foreshadowing of things to come. We're not gonna see it for a few slides, but it will show up. Alright, behold. This is the OG. Again, I'm gonna zoom in so you don't get overwhelmed. This is the equation we've been working with. This is the equation that you all been doing this whole time. Add up, I say this whole time, since last class. 1 over the total mass times the add up all the objects and how far away they are. Great. Well, how do we make an infinite number of them? We make them infinitely small. Infinitely small means that m turns into a dm. dm is just a mass that's infinitely small. dm just means really, really, really small mass. All right, great. Get rid of the integral and get rid of the summation and make an integral sign. Ta-da! And the problem is we also might have to figure out the total mass of the object, so we're going to replace that m with an integral dm. If you integrate all the mass, you get the mass. Makes sense, hopefully, maybe. All right, and here's a pretty picture showing this diagram where r is how far away you are, and dm is some mass that's kind of in a slice of the thing. So this here is the general form for this, and it's going to show up in another slide. And then, yeah, I kind of already... So we're going to see this in a future slide. Don't worry, it's going to pop up again. I'll give you all more time to write it down. Okay. How do I find the amount of mass in dm and relate it to its location? And this is one you kind of already answered. What was the buzzword that you all used? How do you define how much mass is concentrated in some area? Density. So, man, if we can just get a function of density as a like where you're located, if we can figure out the density based on where you're located, that's one step. And then there's one more thing I'm going to have to do to that density. What am I going to do to that density to get the mass? I need to go from density to mass. In chemistry reminder, what is the relationship between density, mass, and volume? Is density mass over volume? Is density mass times volume? Density volume divided by mass. Is capital D density. Mass over volume squared. No, yep. Yeah. Chemistry is just macroscopic physics. But, yeah, I mean, any chemical reaction, there's reasons behind why they react. That's physics. Physics is just like the base understanding the universe. Chemistry is just looking at a specific thing, how elements and things like that interact with each other. Yeah, but it is, the challenge is chemistry at its fundamentals becomes quantum mechanics. Electron orbitals and why they interact with each other on that level. So it's a bit of physics too, and quantum mechanics, and you stir it all together and you get chemistry. Any science is just applied physics, because physics is just how does anything work, and then specific fields are looking at how specific systems work. Really, really complex systems. All right. I believe in you all, so maybe 5 more seconds. 5, 4, 3, 2, 1. Boop. All right, this is just a relationship. It's literally the density is how much mass you have per volume. Now, if I wanted to be really mean, I'd give you, okay, I can't even do this because you don't technically know triple integrals, even though they're very simple. So we're not going to do triple integrals in this class. You could. They're really good. It's just doing, if you had so much fun doing an integral once, do it 3 times. All right. Huh? Yeah, that sounds like, so we'll go to the simplest case. Instead of a volume, instead of a 3-dimensional volume, let's go to 1 dimension. And it turns out that there is something called linear mass density. It's the exact same relationship, but instead of volume, it's length, where you're located. And then there's one called surface density, which is how much mass divided by area. You can figure out how the mass is distributed in a straight line. You can figure out how the mass is distributed over an area. And you can figure out the mass is distributed over a 3-dimensional volume. So, there you go, y'all. Linear mass density. Oh, this is a Greek letter rho. It's a P without a little, so it's not a, no little, I don't know what you call that. It's a P that's at a very slight angle without a little line sticking up. Rho. All right. So, rho equals mass over length. Rearrange that. Just do some algebra. So mass equals rho times L. And then take the derivative of both sides. Density is going to be, we're going to assume we're going to put as a function. So you're going to have dm equals rho dl. Just make it infinitely small. And L is just a variable for where you're located. So just replace it with x instead. Replace L with x. There you go. So here's our original equation. This is the one that's the integral. And the problem is r dm. The problem is mass is a function of where you're located. So we had to rearrange this. You could not do the integral beforehand because it's r dm. R is not a constant, and dm is changing based on where you're located. So you had to fix the equation to be in terms of variables that actually interact with each other. So that's all we did here. We replaced r with x, and we replaced dm with rho dx. And now we can integrate. And we did the same thing on the bottom. So this is the equation for finding the center of mass for an object with a density. And this density could be a constant, or it could vary. This density could be a constant, or this density could vary. And reminder to you all, you may be like, why would the density vary? Reminder to you all that you can model a triangle as a rod with varying density. So you can do clever ways of solving problems where if you recognize that a triangle is just something with like a density that's varying, if they're approximately the same thing, you can use that to solve the problem. A lot of clever physics is taking a system and modeling it as something else that we know how to solve. So, all right, there you go. Here's a nice slide with all the things. I'll leave this one up for a bit. So this is all we need to practice. This is the last thing I need to practice with you all is solving this equation. Because the real world, you do sometimes get point masses. But this is more likely you have a continuous object. Oh, yeah. Yeah. Okay. I would just pick one. I was like, you don't want to do more two. No, because the guy even emailed me. He was like, hey, just in case before, like, we do anything, just come to this faculty showcase to make sure you're doing some. And that's the work of a good advisor. I think he said that too. He's very computational. And he realized that. Yeah. That's really good. No, there is one I need to teach you all about moment of inertia. Oh. Yeah, that's the last problem set. No, because after the exam we'll have like 2 weeks or a week and a half. And so there is a little bit more I need to cover as much as I can. And not to even be cutting some things, but yeah, it's a good question. All right, I did get a really good question that I want to kind of convey to everyone. After test 2, there is a little bit of extra stuff I have to teach you all. So like we're not done with content after test 2. After test 2, I got to teach you all about torque and moment of inertia. Those are the 2 major things that we need to cover. I am nixing conservation of angular momentum because we don't have the time for it. But to prepare you all for your future classes, especially those in mechanical and civil, I need to teach you all torque and moment of inertia. Half of statics involves torque. So if I don't teach you torque, that's not good. All right. So I already mentioned this. Reasons for finding center of mass, rotating an object, figuring out where to put support columns to put the least strain on your system, all that kind of jazz. All right. This is the only problem I'm going to do with you all related to this. Find the center of mass for a thin bar of length 20 centimeters whose mass is distributed according to the function rho of x equals square root of x plus 2x squared. Remember, you always need to define the origin. That's going to come up in your lab today. Where x equals 0 represents the left end. That's my origin. X equals 0 is the left end of the bar. If I do not define the origin, you can get an infinite number of answers that all make sense depending on your frame of reference. Assume that rho is measured in grams per centimeter and x is measured in centimeters. And yeah, draw a picture if you want. This is a fairly complex equation, so figuring out what this equation looks like will be a little tricky. So you don't need to know what the function looks like. But write down your givens, write down what you're solving for, see if there's an equation that relates them, and try it out. And I'm going to leave this for you because I think you all can figure this out given what I've given you. So we'll go around and assist you all, but I think you all, I have confidence you can solve this. I'll put the answer up. So this equation will do it. You just ask yourself, do I have all those things? Yep. That's always when choosing an equation. It really just boils down to, does this solve for what I need? Does it have what I have? Or if it doesn't, can I find those things? Yeah, perfect. If it doesn't need that, then it's a valid equation. The machine works. Integrate over the bar. Oh, sure, what happened there? Yeah, do it yourself. That's what the calculator, that's a black box. It is like trying to cut through and figure out what was wrong. I mean, okay, it wouldn't be good. I would just say 14. And I'm fairly confident my answer, but I'm going to solve it up. Have y'all solved it yet? Is the answer not right? Darn it. I was confident. I was like, I solved this thing a bit back, and I checked my work. But I need to write it out to double check. Can someone plug in a calculator again? Let's go right. Ugh, I'm gonna have to write it out. Yeah, someone else got it. All right, there's a chance that the answer is 0.1497. Yeah, there's a chance you get it. Oh, yeah. All right, great. Yep, okay. I've seen 3 people with this, so I'm not sure what I did wrong here. 1, 4, 9. Oh, yeah. 14.97 centimeters. There you go. So your calculator is right. I've had 3 people get that answer.
Yeah, I got it.
All right, you got your givens.
Oh, that's why I really know. That was the radius.
And then what equation relates all these to? Do you have a density function? You know the bounds of your integral. Yep, exactly. Yeah, you're integrating over the whole bar. You're adding up all these things. Yep. Yeah, exactly. Sure. Yes, that was the derivation. That's what we use to get solved. What's given? I know you got it. Oh. And then, what do we solve for that? We have an equation that relates to that. Nobody answered that. And then what are the bounds that integrate? Where am I integrating from? I need to integrate across the entire bar. There you go.
In this case,
Yeah, that looks good. Let me start writing it out. All right, so let's start kind of writing it out. Depending where you're at, I'm hoping most of y'all are kind of plugging things in. If not, we're going to find out. So we have our density function, square root of x plus 2x squared. We have where our origin is. That's our left side. And then we have the final x position, which is 20 centimeters. We are solving for the center of mass. And we have a very handy equation that I've given you all that relates the center of mass to density, which is 1 over the integral of rho dx times the integral of x rho dx. And again, don't lose track of what you're doing. Don't just do math for the sake of math. What I really want to encourage you all to remember, what is this doing? The first term is just 1 over mass. If you integrate density times where you're located, it gives you the total mass. This gives you the total mass. That's the whole point of that first term. The second term, weights. So this is kind of like my R, and then these two terms are my dm. You don't need to know this to do it, but it is very easy to just do math and not think about what you're doing. And I want you all to remember that there's physical things that these represent. And if you do that, if you remember that, that means you understand it better, which means you can apply it to more situations. Just doing a bunch of math is boring. And you don't get much meaning from it. And you can't apply it to new things. In a physics class, you need to know what the math means. If you do not know what the math means, you're just a robot. All right, so our center of mass equals 1 over, and then we put our integral from 0 to 20 of square root of x plus 2x squared dx times the integral of x times square root of x plus 2x squared dx integrated from 0 to 20. And then we're going to integrate, we're going to simplify this and then integrate it. I'm going to get another slide because there's too many things that fit on one slide. So as a reminder to y'all, once you get to step 3, the rest is just math. But I do need to make certain you all can do integrals. Integrals are something that are fairly new to you all. Like you've only learned them in the past few years. Algebra, I didn't worry about as much because algebra is something you've been doing since like middle school. But calculus is new and exciting. All right, so x to the integral of square root of x ends up being x to the 3/2. And you chuck a 2/3 in front of it. Make sure it stays on the bottom though. How do I cancel out? So I'll let you all think through the integrals. I'm not going to. X to the 3rd. And that needs to be evaluated from 0 to 20. And then on the right side, I'll write an extra step for funsies. X times the square root of x is x to the 3/2 plus 2x cubed dx. Yeah, from 0 to 20. And then I'm going to integrate that for funsies. One over 2/3 x to the 3/2 plus 2 over 3 x cubed evaluated from 0 to 20 times x to the 5/2, and I need a 2/5 in front to cancel that out, plus 2x to the 4th, and I divided by 4 to cancel that out. Everything's evaluated from 0 to 20. You put 0 in, everything goes away, so we're just going to put the 20 in. That's all we need. All the x's. I could factor out x's. I'm not going to. I would do that if it was me, but because I wouldn't want to write this much. 2/3 times 20 cubed times 2/5 times 20 to the 5/2 plus 2 times 20 to the 4th divided by 4, close the parentheses. And then you plug that nonsense in a calculator. Yeah, this is very much one that, goodness, you cannot do this in your head. Like, write out the steps. If you do not write out the steps, you're going to do stupid stuff mathematically. Way too many things on this page to do this in your head. Every single time I wrote something down was an opportunity for your brain to forget something. And this is also the benefit of a calculator that lets you see what you typed. I am typing so many things in my calculator right now. I'm plugging this entire thing in my calculator in one go. Get a good calculator. All right, great. I got the answer. Good job, me. Well, I got the answer after the other people realizing I had the wrong answer before. 14.97 centimeters. We did not have to convert units because everything's working within the same units. So we're adding centimeters and multiplying centimeters. We're not multiplying any variables times any other unit. Everything in this entire problem is in centimeters. Every single unit, it's all in x. So the output is in centimeters. If at any point I multiplied by grams or I multiplied by anything like that, then it doesn't work. So that we did not need to convert it. If you really, really wanted to, just put a 0.2 in front of these, and then that would be in meters, and that would be fine. So it's always better to play it safe. If you wanted to convert your units to meters, and then that's always a safer option. Instead of asking yourself, when do I need to convert units and when do I not? Just always convert your units, and you'll end up in a safer boat with no leaks. Okay, so it's all there. That's that. That's the last thing I need to teach you all. There's like a couple more problems of this in the problem set. So there's one more you all get to practice if you want to. This one is just all in terms of variables. It's a fun problem to do algebraically. Like, it's good. But I'll tell you all, this is the only one I have like this with a density function. If you want more of them, 14.97. Make your own and then have ChatGPT generate a solution for you to check. It's pretty easy to make these problems. Do the exact same problem, set new bounds, make a new function. Make it an integral you can actually do. It's really easy to make an integral that you can't solve. So don't do that. Okay. For now, y'all take a breather, ask me questions, whatever you want to do. We'll do the lab in like 5 minutes time. So 9, when these clocks say 9:10, we're going to do a center of mass lab. They're going to want to put tape on the sticks. So if I can do this, you can do this. I don't know if he does it. That I'm just going to tear off. I only have one roll of tape. So the solution is we just put a bunch of strips of tape here to make it flat. And we hope they don't stick to the tape. So someone to do that, and then the mass sets are in that cabinet, which might be locked. Oh, okay. Whoops. wraparound. Yes and no. So the challenge is they're going to have two separate locations where it's going to balance. Yeah, and if they need more, we can always do that route as well. For masses, they're going to need two different masses. And I'm just going to test this real quick. The good news is they don't need scales today.
Well,
They're
there's
building.
one part where you said where the
Oh, okay. I do have them actually check it. You're okay, so we might need this. I need to see if this changes the center mass by an appreciable amount. I'm also assuming that the center mass is actually 1050 centimeters, but it's not.
It's not.
Which is fine. I actually want them to find it. Okay, so now what I want to check is that this mass is going to change the center mass by an appreciable quantity. The more it changes it, the less error there is. So that only changed it by about a centimeter, which is mediocre. There's bigger ones that we can use. I did want to use one that was too big, but I didn't know until I came here and tested it. What is a So here we have 50 gram masses, which is double. So this one bounces about here. If I place this here, oh, that's nice. Yeah, 50 grams is fantastic. Yes, perfect. Then they will need another mass that's 100.
Yeah.
I want this to be here. They could use a 25 as well. Actually, 25 would be perfectly fine in this case. But then we're mixing and matching mass sets, which is unpleasant. Or they could start with 100. Nice. I like this one a lot. Okay. So if they use the 100 gram one, it actually works out pretty well. And then if they want to shift this back, the 50 gram ain't gonna cut it.
So when I have this, could I use just a top one? Plug in the top.
Okay. So you can't do that. But they could use a 200 gram.
Okay. So if it was another that it was 0,
If it was 12, you would do this backwards. Minus the whole thing again. But it's 0.
Alright, that works out really well. 100 and 200, I think, is the magic sauce.
Okay.
Here, it's just whether or not we have enough.
Sure.
Yeah, there should be a whole set of them in there. Because the bigger the mass, the more it's going to be farther away.
You need help.
They might need more.
Yeah.
But I will need it. So one of the major things that they need to do, and I will tell them this when we come up with our experimental design, the first mass needs to be smaller than the second mass. The first mass has to be smaller than the second mass. Otherwise, when they do part two, it gets awful.
So if they're all using the same two masses,
I think,
grading is so much easier.
yeah, I'm gonna warn you. And so we could tell them to use the 100 and the 200. If you all want to organize those.
From here?
Yeah. Okay, I'm gonna go ahead and delete the lab groups, if that's good with you.
Yeah. Last time was also easy because there was like one group that hadn't checked off.
Yeah, and it is nice that I can output the lab groups and do
That
the.
was so scary. I was like,
Yeah. There's always a way to automate, like, through the power of data analysis, there's always a way.
How many groups do we have? How many groups do we have?
usually we have like around 30.
30 groups.
Yeah.
A lot of math. 1, 2, 3.
There's, I can see some more peeking out.
Yes, I can get one.
I could have sworn I updated this, but clearly that is not the case.